Hi there, we're live coding again, and now we are continuing where we left off. The last stream was just a couple of hours ago, and what we did then was to teach the Studio user interface to search for Nix package definitions. It was a step towards tighter integration between the two halves of Studio, where the front end half is a Pharo Smalltalk GUI, and the back end half is a Nix API. And what we want to do now is to take the next step and get the Studio front end to have a bit more visibility into what's actually going on in the back end. So if we fire off a build with Nix, it might take a second, it might take a minute, it might take an hour, it might take a day, depending on what we ask it to build. And we'd like to have a little bit of visibility into what's going on and see the progress and that kind of thing. So let's dive right in. This is the to-do list we had from earlier. We did that. Thought of something we needed to contact upstream about, and I created an issue for that. And now we're here. We want to see build progress. So if we pull up the Studio UI, keep our feet on the ground here. If we say Studio Inspector open, this is our window where we ask Nix to do something. So suppose that we would ask Nix to sleep for 10 seconds. Then we click the green button, and what we expect is that it takes about 10 seconds for this, I don't know how well you will see it, but for this to finish and give us a result. And I guess that this will actually give us an error because it's not going to create any output, which I'm going to be happy about. But anyway, at some point we're going to wonder, is this really doing what we want? And particularly if you ask it, if we ask to run a Raptorjet program, for example, which is a common thing that we do, it might run very quickly, but it also depends on the state of our machine. If we've just upgraded Studio, it might be that there's a new version of the Raptorjet VM available, and that the first time we run an expression, it's actually going to go off and fetch that and build it. It might also be, if we've updated the package collection for Studio, it might be wanting to build things with a new C compiler, and then it might need to rebuild all of the various packages. So generally speaking, when we ask Nix to run a build, it's going to build all of the dependencies, and that means it can take a while, and we want to have visibility of that. We don't want to just sit here, wondering what's going on, whether it's stuck or whether it's going forward. We want to have a little bit of visibility. And let's say there are two main ways that we could approach this. And what I want to do now is take the kind of the hard, possibly impractical approach to get a better feel for it. And then if we don't like that, we can fall back on the simple approach. The simple approach would be to just run Nix and take the output that it prints and print that, the same way that you see it in the shell. That would be pretty straightforward. And so often Nix builds involve a lot of parallelism, and that can make the output a little bit tricky to read. This has actually been improved quite a lot in the new version of Nix that's coming out, and we could use that, so we could get it reasonably pretty. But what I thought is we have this really nice high-level Smalltalk environment here. Generally speaking, if we import data into the Smalltalk universe, often we can do interesting things with it quite easily. So what about if we went more on that route? What about if we want to build something with Nix, if we first got Nix to make a plan of everything that needs to get done, all of the dependencies that are in play, and then we would parse that or load that somehow into the front end, and we would see what's already built versus what needs to be built. And maybe we just poll that while the build proceeds. So we would see, maybe for each package we would say, is it already built, is it not built, or is it currently building? And maybe if we clicked on a package, we would see the status of that build specifically, that kind of thing. I think that could be a neat interface. And I think also that being able to interactively inspect the Nix store could be an interesting direction to go in, as we do more with Nix and we want to do interesting things. It could be an interesting direction to go in. It could also be a kind of a complicated detour and a kind of a really roundabout, impractical solution to the problem. And if it starts to look that way, then we'll fall back and we'll just print the output from the next process. But that's what we're going to try now. So here we have our inspector, and when this runs something here, it calls, hold on, Studio, let's see what it does. If I run Studio Inspector, if I browse that class, it has a go method, which is what runs when we click on this little green button. So it will, the class called Nix build, it will say Nix build on code and give it the text we entered as a string. It'll take the first output for that, and then interpret it as if it were a wrap-digit process, which is a little bit specific. But anyway, so what does Nix build do? You give it some code, you tell it to run. Okay, but this is interesting actually. So it's already doing this Nix Instantiate. So what Instantiate means, so normally with Nix, if you want to build something, you say build this expression, where the expression is a Nix expression, which is a purely functional program. And that's actually implemented in two steps. The first step is it instantiates the expression. That means that it runs the Nix code and produces a set of, they're called derivations. These are things that need to get built. So it might have a derivation for libc, a derivation for GCC, a derivation for, you know, the virtual, for a lot of things. Everything that is relevant to producing your output is there. And yeah, each derivation becomes a file on disk that describes what needs to get built and all of its dependencies. So the derivations depend on each other in a kind of a directed graph. So that's instantiation. After instantiation, you go from having Nix code to having a set of derivation files on disk. And then the next step is to realize the derivations. And that just means to just put them into build the directed graph and build them in dependency order. You know, building will involve you know, running some commands in a sandbox and storing the result in the Nix store. So what I'm thinking here is, the first step that we want to do is this instantiate. When we have an expression that we want to build, we want to instantiate that to find out what are all the dependencies in play, what's the dependency graph, and then I think it would be nice to visualize that. And then the next step would be to mark each of those dependencies on whether they are, you know, built or being built or not built yet. So why don't we try to do that? We'll try to Nix instantiate some code. Let's just try calling that and seeing what happens. If we would just interactively write a bit of code here, if we say Nix Instantiate with import studio wrap-digit.run, so we tell it to run a wrap-digit program. This is an instantiate, so we don't expect this to actually run. We expect the Nix code we have written here, we expect this to be translated into a derivation file saying what needs to be built without actually taking the step of building it, because that's what instantiate means. Let's see. If we run that, what do we get? We get paths, two things that need to get built. These are .drv files, which is a Nix derivation. So if we would take that and convert it into a file reference and inspect that, and we can see the contents here. So this is, I can't remember the name of an A expression or something. This is a Nix internal format. There is a pretty printer for these somewhere. But anyway, this is an on-disk representation of something that needs to get built and all of its dependencies and a few other things. I don't remember the exact format. So this is a good step, right? So this is a recipe for something that needs to get built, and it's referencing a lot of other recipes by the look of it. And so what we want to do is get this into a neater format, something that we can understand in the Smalltalk VM. So it's actually really nice to write parsers. There's this thing called PetitParser that is a beautiful parser generator, but I think that will be massive overkill here because I'm guessing we can find a utility that prints this in some other format that we can already parse, like JSON or XML or something. So let's check that, shall we? So Nix Instantiate. there such command? Yes, Nix Instantiate. Minus minus XML. I mean, that sounds promising. And minus minus JSON. But let's just see what we would get if we did that. Maybe we'll muck around on the command line for a moment, actually. Nix Instantiate an expression be with import video. How do we run it? How do we run it here? Made a temporary file. Here we just ran Nix Instantiate on a file. Well, let's make this into. Oh, hang on. Do this. We know that the stuff we want to import is the current directory. Where is this? Don't need that. So we didn't get any XML output there. So is that because we didn't ask for the right thing? I think we can actually get a few. Minus minus eval do. And we want to evaluate this all the way through on the Nix level. We want to evaluate this to the point that it gives us derivations. And you know, Nix is a lazy functional language, so it doesn't necessarily. That's what we want. Ask it to be strict and evaluate everything. We'll try a couple of things and see. That forces everything to evaluate. That looks promising. It's big anyway. And 90,000 line XML file. Okay, let's see if we can parse that, shall we? Here's where we have it. Try to get that as a file reference. Memory are we talking about? Gigabyte. That's considerable. Even as an intermediate format, I don't think. Okay. I guess that when I said strict, maybe this maybe this went really deeply recursive. And well, maybe there's a lesson here. Maybe this is the kind of the complete closure of all of the referenced software, which might be most of the whole distribution. So maybe that was maybe that's what maybe this is a be careful what you wish for situation where we asked for the complete tree of all dependencies, and that was just really big. I think that's pretty plausible. So maybe the first thing that we saw was more like what we want, and we just want to have it pretty printed actually. So if we go back to that first thing that we had, or any really DRV file, here's just some random derivation file. So probably this is what we want, in the sense that this is one node in the dependency graph. So even if the dependency graph is super duper duper massive, this is just one node and the edges out of that node. So then at least we would be traversing the dependency graph in a way that suits us. Yeah, no deeper than we need to go. So we might be able to construct a tree view, for example, where we can click our way through, and even if the whole tree was too big to expand, it wouldn't matter, because we would never want to do that anyway. Okay, then in that case we just want to get this in a nicer format. So then I think we do want this, I think it's called an ATerm pretty printer. Nix ATerm pretty print. I think that there's some random package that has such a beast. pp ATerm. Otherwise, we could also just parse it. It's actually really nice to write parsers in Pharo, but most of the time when I do that, I realize there was an easier way. Pretty sure. There seems to be a Haskell package to do it, but it seems like then you end up downloading a gigabyte of Haskell universe, which we probably don't care about at the moment, actually. We're to a first approximation, we're just going wild and crazy with dependencies, because the Nix manages to import them in a disciplined way, and I'm kind of doing a hand wave and saying that at the moment, at least, I expect Studio to be running on a kind of a server class machine, something with a fast internet connection and plenty of disk and plenty of RAM and everything. So I don't really bother about trying to minimize dependencies at the moment, although that day will surely come. So what about if we try running that? And then we got to find out whether the internet connection I'm on here. I always imagined that I would do most of my studio work on like a Hetzner machine, which has a gigabit internet connection. But this is actually running on a server in my basement, so it's on a plain old DSL. And I want to give that some parallelism. That's going to be 70 megabytes to download and a gigabyte of space unpack. At the moment, we don't care, actually. That's fine. So it's quite a bit. Anyway, we'll see what that gives us. And this would be something we could easily replace with our own parser if we need to. See what that gives us to start with. In fact, this is a pretty printer, so depending on what its output format is, we might have to parse it anyway. If all it's really doing is making things easier to read for humans, we need something that's machine readable. We'll see whether that's what this provides or not. What was that? That was the Glasgow Haskell compiler. So this is nice for the current purposes now of understanding what's going on. This is nice because it's pretty printed the thing, but I think it's in the same format. I think it's only changed the white space. So it is just a pretty printer. So this is not. Well, we can see it has some arguments, because what we would like is a conversion into some easily parsed format like JSON or XML or something like that. We can do a HTML. That doesn't sound any better, I gotta say. So this might not be the program that we're looking for. But anyway, if we run that on one of the derivations that we were looking at before, where's one of the ones that we actually... Here was one. It was for Raptorjit thing. So let's just see what this says about Raptorjit, just to make things a little bit more concrete. Pretty print the Racket derivation. Scroll up a little bit. So to interpret this, I think we actually need to open a beautiful document that I highly recommend, even though it doesn't sound like something you would read for fun, which is Elko Dolstra's PhD thesis, which is just a beautiful description of the whole Nix idea. And for me, this is what really sold me on the whole thing, just to see this very well thought out, very well thought out and good design. And I think we'll find a grammar for ATerms, I think they're called. There's an example. Grammar. Is it right to search for ATerm, or should we be searching for something like grammar? Not interested in the Nix. In the table of contents. I guess the index. Go up in the index. PDF has probably got a nice index. It's 40 and 105. ATerm sensation. That's what we have. Textual ATerm. Not completely satisfied with that. What is the syntax of a Nix ATerm? Come on. I'm not finding it. Okay, that's slightly disappointing. So it might be that this ATerm format is traditionally considered kind of an internal thing in Nix, and that it's not very often that people actually want to go in and parse it and do things with it and manipulate it. Perhaps normally you would do that inside Nix. The thing about Nix is that it's written in C++, and I have a lot of resistance to hacking C++ code, which is a pity, but that's kind of the way it is. My perception is that when you write an open source project in C++, you're kind of limiting its appeal, certainly limiting its appeal to me. So we're going to consider doing this the hard way, but if we are going to parse this, we're still going to need to know what its format is. But we can see that it's basically some kind of a tuple, right? A list. We need to get the format of this. I mean, this looks quite reasonable to parse. It would probably be a fun exercise for right now, even to parse this using the PetitParser, because it is really nice. We could actually figure out the grammar after we did this, right? Because it looks, by inspection, it looks like it's very easy to parse. So if we're confident that it's worth parsing, then we could kind of shoot first and ask questions later, and just convert this into a parse tree. So, question then, I suppose, is this going to tell us what we want? What we want is to know. This is supposed to be a description of the result of running a Raptorjit program. So what we expect here is that this derivation has to run a Raptorjit program. So it should depend on the Raptorjit virtual machine. So there should be a reference in here to a very specific version and build of the Raptorjit virtual machine, and a few other related things. And there should also be a description of the outputs that this is going to produce. So long as that is there, then I think that this contains the information we want, and it's worth either parsing, or we have another quick look before we write that, another quick look at if there's anything around that can convert this into some other format already to save us the bother of parsing it. But let's just see if we have those things. Okay, so this is the name, Raptorjit eval code. That sounds like the name of the thing that we're building here, an evaluation of some code. This looks like it's probably the inputs that we have. Bash is probably used for running a shell script that makes Raptorjit run. Script.lua, this sounds like a file where we stored the source code that we want to run. So this, where do we have it? Added some code. It wasn't that code, it was some other code. Somewhere. We had this Lua code here. Nix. The Nix code will have written that into a file, which would have been the script.lua that we saw. And then Raptorjit audit log. This will be a specific version of the Raptorjit virtual machine built off my audit log development branch. And standard env. Okay, so that's an indirect reference to the standard environment, which would include things like GCC and all that kind of stuff. I don't know if any of that is needed there, but this kind of looks right in terms of inputs. We know what it is that we want to build, and we know all of the things that it depends on, and we have these references. So what we're looking at now is one of these .drv derivation files, and we have a list of all of the other ones that it depends on. So it actually looks like we can build our dependency graph from this information, right? We say this is our ultimate goal is to build that, which is described in this file that we're looking at, and that has 4 dependencies, which then in turn have dependencies, and there's a whole tree out there. So if we wanted to get some visibility into what's going on in the Nix store while a build is running, we could presumably use this file to spider our way out to a certain relevant depth, how far we want to go in the dependency tree to see what is it that what are the things that are dependent on by this. Then we can see which ones are already built, and which ones are currently building and which ones are not built yet, and that would be some kind of a progress bar actually. You know, if we would run a build and it would show the tree, expand it out to show everything that needs to be built, and then, you know, mark the things that are currently building, and then maybe collapse the tree as builds complete until you end up with just one thing at the top. Something like that would be really cool. So we're going to have one more quick look for a way to convert this into XML or JSON or something like that to save us writing a parser by hand. And it's funny as well, because when I say something, we could use any program from anywhere, because we're tracking all of our dependencies with Nix. So I mean, God forbid, if we would find a Java program that could do that, it would actually not be a big deal to pull that in and have it as a dependency, because Nix just takes care of dependencies. So anything we can reference with Nix is fair game. So we in that sense, we want either something that's purpose built for the task of translating Nix A expressions like this into another format, or kind of anything else that can do the job really easily. And in lieu of either of those things, we're going to write Smalltalk code to parse this. So, all right, one more time. Let's look for a Nix ATerm to JSON. To XML. Nix. There's a Racket library. Is it the same ATerm format? What does that look like? I mean, so Racket Scheme by Dave Homan, nice guy. Okay, so Racket Scheme would be a pretty kind of arbitrary dependency to have, but it wouldn't actually do us any harm particularly. And this actually kind of looks. This is the Nix ATerm format, and Dave has apparently actually found a description of that somewhere, so he did better than I did. So I wonder what this outputs. It would be kind of amusing to pull in a dependency on Racket to translate ATerms into another format, like something ironic is like using a nuclear weapon to crack a nut or something. But if we actually had to write code, even a couple of lines, then that would be a little bit much for me. I don't want to actually be programming in Scheme just right now. It's a little bit more than I want to be doing. So let's look at that description that he referenced. That is gone, but that was from Ratigox. This is some old archaic piece of software. Did I misspell that? Language and toolset for program transformation. I don't know if this is the same thing. It seems plausible. So, I mean, here we are, one of these forks in the road, right? There's a few different paths we could take. We don't really know which one gets us where we want to go the fastest, or how close we end up to what we would really like. So we do an A-star search, and we'll kind of make an estimate of how close we think each one goes. My gut feeling is that since we didn't find anything off the shelf to convert from a Nix ATerm into XML or JSON, that would have been the ideal. Something that already existed did the job. We found a pretty printer, but that was only changing the white space. It was still keeping it in ATerm format, and it was quite large. It had a gigabyte of extra dependencies to install. And now we're looking at more elaborate things, like we're talking about maybe writing scheme code or something, which seems like a bit of a detour. I think we're gonna The first path we're going to go down and see if it becomes tricky is to just write a parser in Smalltalk, because that's a nice thing to do. We're already doing Smalltalk programming, and we're going to be parsing things in the front end, a lot of different small things. So generally, sharpening our Smalltalk parsing skills is something that would pay dividends. I think that's actually the reasonable thing to do here. So we're going to use a parser generator called PetitParser2. I've written a few parsers with this, and every time it seems like I soon discovered a way that I could actually solve the problem without having a parser. So this is probably going to be the same again. Probably we're going to write a parser, and its whole lifetime will be a week, and then we'll find that there was something off the shelf. But whatever. This is live coding. We may as well do some coding, right? So this is the parser we're going to use. First, and there's kind of two ways to write these parsers actually. There's the kind of the right way, where each production is a method on a class, and you have a unit test for each production and that kind of thing. But I find this is not the way that I like prototyping anyway. The alternative way is just as a flat workspace, kind of like pretending you're in a REPL or something, and that's the way that we're gonna do this one. So let's get our input, shall we? We'll take that one we're looking at here. We'll take the non-pretty printed version. Maybe we already had that, did we? If we say, yeah, so here, this is something that we want to parse right here. So that is a file reference. If we browse that as a string, I'll open a new inspector for that. So what we have here is a so-called glamorous inspector on a string, and that string happens to be the input that we want. So we can pop over here, and we see the raw view of that string, and we also see character by character. We also have a little workspace here where we can write code. We can write code that. Hang on, sorry. The workspace is the appropriate way. Let's just get started. We'll transport it into its own workspace later. So we're going to say input current object, and is that just going to give us the string itself? If we run that, I think that runs and gives us the same string. Yes, good. Okay, so let's parse something. We are gonna, first thing, we're gonna have a production called derive. I hope we don't have to actually declare everything. Let's gambit that we don't. I think we do. Derive production is going to match the string derive. So there's two versions of the parser, version 1 and version 2. I think for one you write as parser, maybe not as Pparser. Do we have parser loaded? No. Okay, we need to install the parser. It's not in our base image. That's a pity. How do we install it? Like this? We will run that. And we'll go off on the internet and grab the latest version or a recent version of Parser framework. Another time I can explain how we build up our Smalltalk image with all of the libraries that we want. There is a medium-length story about that, but for now we're just going to pull this in. That's still loading. Okay, now that has loaded. Now we should have methods like as p. I think you're right, as Pparser. Sorry, no, this is still down. Oh, okay, so it had some dependencies of its own, and maybe those were newer than the things that we had. So another time what we'll do is we'll update our base Pharo image to include the latest versions of all of the things that we depend on, like this Rossal drawing library and the parser framework and all of that kind of thing. For now, I'm running probably pretty conservative versions in the base Studio distribution, and now when we load the latest version of some other library, I guess it goes off and wants as dependencies to load newer versions of everything. So what that means is the code we're ending up with in our Smalltalk image here is probably different, quite a bit different than what we're normally running when we start Studio, but that's okay for now. Okay, while that loads, we'll find, just blindly merge that and hope that it works. We will find documentation examples for this. This parser generator. So this is like a but I'm not up to date on all the right names for everything. This is like parser combinators. It's also like a peg, and it's got some very interesting features. This star lazy I won't digress into now, but it's actually got some really nice features for when you only want to partially parse things. For if you have a file, you know, some nasty format like PDF or whatever, where there's some very specific things you're looking for and you want to very explicitly parse those, and you want to ignore everything else. So that feature we probably don't care about now because it's a simple format that we're probably going to want to parse completely. But there are some actually really interesting features in this. Okay, so that has hopefully loaded. Now let's see, do we have methods like as pparser? Yes. So the way I think that this works is we have a string derive, and if we ask for that as a pparser, then I think this is now a parser object, and we can ask it to parse a string, and if the string is exactly derived, then it will succeed, and otherwise it won't. So if we test that, derive, parse, derive, is that something that will succeed? It looks like it. If we would ask it to parse derival, then it results in a parse failure. Yes, so we have the first step of our parser. So if we say that parser is derive, you might be able to use this star lazy. You might actually be able to use this incrementally. I'm hoping that star lazy is just going to ignore everything that comes afterwards. So I see on the chat now that Dolman has left a link to some information that might mean that we're on totally the wrong track. But I'm starting to have fun now, so I mean, you can always spend an hour or two having fun, right? So we're gonna work some more on this parser, and if we get stuck or we stop having fun, then we're going to go back and see what that tip was. Anyway, away we go. Now we have a parser called derive. Then we have a parser that is a derive star lazy. I don't really have this swapped in at the moment, but I'm hoping that that's going to parse some number of these. Going to parse that as many times as it can in a string and ignore everything else, and we'll see then if that can succeed on the input, which is the A term. Yeah, by the look of it. So it looks like it succeeded and it gave us the string derive. So I think that what we have here is basically a parser that will match the string derive 0 or more times in a sea of anything. So now let's make it a step more clever, and let's make it also handle parenthesized lists. And let's pull up that Racket code again, just for reference, because they had some productions there, right? We're going to call this a Topol or Topol, or however it is we say that in Australia. I can't remember. I never knew, actually. I got the word from programming with Swedish Erlang programmers. Anyway, we will say that a tuple is an open thingy and followed by an open parenthesis as a parser, followed by a I'm not sure if we're going to have a problem with this recursion, are we? Since I'm writing all of this in a kind of a flat little bit of text here, I hope. We're going to just make that garbage. Okay, skip as much as you can. And to think about whether doing this all flat in a workspace here actually prevents us from making recursive rules. I'm not sure about that offhand, Bill. How about that? And then should we say parser is derive, and then it's a tuple. Might just be one tuple. Let's see what we get out of that anyway. Let's see if anything happens when we're on that. Sequential. Oops. Oh, okay, that didn't work. We have on the chat. We have a vote from Australia that it's a tuple. Tuple. I would have said tuple. I'm sure when I lived in Brisbane, I'm sure I would have said tuple, and I got tuple from somewhere. But tuple, that sounds American to me. Anyway. So the thing here is that I need to define these things recursively, but when everything is defined in a local variable like this, I don't think there's enough indirection to make that happen. So I think despite my best intentions, I think we maybe have to put this into a class. So let's do that. It's not the end of the world. It's not the end of the world to do things the proper way. I have something here to be reasonable. Okay, we're going to do something like this. We will create something. And and we'll find our package, a Nix package. Here we will create a class called Nix Parser. And this will be a subclass of EP2 composite node. There aren't too many of those scary names we need to worry about. I've learned the hard way in the past that we're going to need to have an instance variable for each production. We might just pre-populate this with the ones that we can think of off the top of our heads. We're going to have a tuple, a list. What do they have? What were the names of the productions? Another one. We have some constant constructor tuple list string integer float. That is something like the set of productions that we're going to need. So whenever we have something needed to invent a new one that's not on that list, we will need to come and update this list. That's fine. So, good. And now we will make a method. Start with this derive method. That's going to be the string derive as a parser. That's our first production. And maybe we will be good and put in tests for these as we go. We will also make a test class. I'm not really into this whole test-driven development thing, but we're going to do it because I mean, it works, right? It's just not that exciting. Enough excitement in our lives, I think, other ways. We will make the new call of that, create our test class. Give that a message parser class. Fine. There is actually a little special IDE that they've got built in here, like special purpose for writing parsers and stuff like this. I just have always ended up getting confused when I use it. You know, sometimes the tool is just the thing. It's makes simple things easy, but then sometimes it also makes hard things harder because you're a little bit more disconnected from what's going on. So I'm doing this the kind of the manual way. It suits me a bit better. Okay, and I'm going to write a test case then. Test case called test derive, which is gonna self parse derive with the rule called derive. And we run that. Instance of Nix ATerms parser did not understand integer. Who was asking integer? Did we do these parts right? Looks like yes. Okay, sorry, let's try that again and go in the debugger and see what's all that about. You know, this might be a double biting thing. So you need to have a one-to-one. Something I learned the hard way a long time ago is you need to have a one-to-one mapping between productions and instance variable names. But maybe the thing is, I knew that you needed to have an instance variable for every production for every method, but maybe you also need to have a method for every instance variable. So why don't we just scale it back? We only have one production method at the moment. We'll try it with only one instance variable and see if that was the issue. Looks like it. Now we've got something else. And we don't implement the method start. Okay, so let's do that. And now we can start with derive, if that helps. Yes. Ah, how nice. So, okay, so we have a unit test that tests that the derived production parsers derive. Okay, not very exciting, but this is, we can go kind of stepwise this way, so it's not such a bad way to work like this. And now we want to do a tuple, right? So we'll define a method called tuple. Well, let's define something called, let's define our top level thing is going to be called ATerm, let's say. We're going to say ATerm is, and now it's going to be, no, sorry, let's say term, because ATerm, I guess, is the whole top level thing that starts with derived. Term is just going to be one of the things that we recursively match, like a tuple or a list or a whatever. And for the moment, we're going to keep this simple. Term is going to be, hang on, let me not confuse myself. Let's do a tuple. tuple is, we'll tighten this up later. For now, we'll say tuple is open parenthesis, and we'll use the star lazy thing, which I think, if I remember correctly, is just going to skip. Basically, what it's going to do is it's going to skip anything it finds until it matches the next thing that it wants, which is going to be the close parenthesis. I think the idea here is that the kind of the peg parser logic is just going to just skip over anything that we haven't figured out how to parse yet, which is kind of nice, I think, right? Then we're going to want a test case for that. Is there actually some key we can press to hop over, find a test, generate test? That sounds. Did that happen? Did that work? Yeah. It didn't do much, but it did something. Okay, fine. Test tuple will be. What did this one look like? Be very similar. Is for now. The notion of a tuple is pretty simple, right? It's just we'll do two, right? We'll do one that's just empty. One. We'll do something meaningful actually, because you know, even though we're cheating a bit now, later we might be able to reuse these tests for something that actually is actually working fine. Unable to parse just an open and a closed parenthesis, and that's because I used the wrong derivation there. Of course, this should be not derived but tuple. Now what about tuple not found? We didn't have, probably not declared our instance variable. Boring busy work. There's probably a better way to do that. Someone who knows Pharo better can tell me. Probably forgot to return the path. Yes, we did forget to return that. That was actually a very helpful error message. Unable to parse 42, so my star lazy thing didn't work. Is it that star lazy has to match something in particular? Is it something? Let's hop over to the example again. Any star lazy, okay. I don't know where any comes from exactly. We'll hope that that's magic somehow. Where are we in? An instance variable. Slightly uncomfortable about that, but what happens? Okay, any. So where does this any come from? Did they define any, or is that something? Is it? They did define any. Okay, fine. We define any. Oh, okay. Oh, right. Okay. Any is you take the symbol any and you ask for that as a parser, and there's going to be a method on the symbol to match anything. Fine. We want a production called any that asks the symbol any to turn itself into a parser, which will know how to do the right thing. Fine. Now it worked. Now that parsed. Good. So we've got derivations and tuples, even though we're ignoring everything inside a tuple. So what comes next? Derive, and then a tuple, and then something which I assume is a list with a square bracket. So what's the list syntax? See here, comma delimited list. Okay, so to begin with, the list looks an awful lot like a tuple. So we will just implement it as such. We'll tighten all of this up later. List is just a tuple with square brackets, as far as we are concerned. And test case for list then similar. Sometimes you really wish you were in Emacs, but not the end of the world. I could learn how to do search and replace in this editor. List not found. That's probably the same mistake that we made before. Good. Now we're parsing the word derive and tuples and lists without caring about the contents. What is next? Derive, list, tuple, then sorry, a tuple and a list, and then a tuple again, and now we have a string. I think we see two quotes there, but I think that that's just an escape. I think that's just the way that Smalltalk prints it. I think we're looking at a string, which is probably delimited by just quotes. Yeah, that's how it really looks. String that's delimited by quotes. Good. Let's put in a production for parsing strings then. And how do we do this? We want to add a production. We've got to put an instance variable there. We've got to make a method string that is supposed to match. I wonder if there's any escaping in ATerms strings. Let's have a look over at Dave Herman's code. Thank you very much, Dave. Which was here. Does he recognize any string escapes? Okay, we'll assume that we can find a grammar description and come and tighten this up later, hey? So now we're gonna suppose that strings are. We'll have a string character as a parser, and then we will have a. I know we're going to regret this. Anything, and then a string. So a double quote, and then we don't care, and then reaching another double quote. And this star lazy, this is magic, right? So this is gonna, if it fails to parse something, it's going to be creative and try to just skip over stuff, and that's probably fine to begin with, actually. But it's not. We're going to want to eliminate all of those once we are actually parsing things. We're going to want to eliminate all those star lazies when we're confident that the parser should match the whole string. But that's a long way from where we are now. Now we want to test that. What generate, test, and jump. Control H, Shift J. No, I think no. Hey, Control H J. We have, I guess, an empty test. Fine. Okay. What is it? What are the tests look? Self parse something, rule something. Fine. Yes. I guess we could be a little bit more fancy and actually test that it rejects things that are not strings. But again, let's just get where we're going. What's next? Hold on. We're actually starting to get kind of close to handling everything, right? Like we're not actually explicitly handling commas. We're not. We're far from it, actually, because we don't have the recursive aspect in our grammar. What we're saying is that's what we need to do next. We need to make. Now we need to really define a term so that we can recurse in. We don't want to just see a tuple and ignore everything inside. We want to we want to recursively parse. So we need a recursive rule, which will be called a term, and a term will be, how do we express alternatives? I think it's with a slash. Something slash something else. not mistaken. Try that. A term is a string or a list or a tuple. We've got to put numbers in at some point. We don't have any in our input, so we can't immediately test that. That's going to be a little bit boring to test in the sense that we'd like to we've already got tests for those separately anyway. We won't write a test case for that right now, actually. We will instead use it in something else that we're going to test. We will say that a tuple is... Now I'm going to take away the star lazy thing. Now we want to say that a tuple is an open parenthesis and close parenthesis, and then what do we want? We want to have a term well, I think we have I think we want to have something for terms, right? How do you normally do that when we want to have things that are separated by commas? I think we're going to have one that has something called terms that is a series of terms. Okay. Term is one of those, and terms is either one term or term followed by comma as comma parser followed by terms. Hang on, not handling the case where we don't have things, so we don't want to. Well, I'm rusty. So we want to match the case where you have where terms is empty. We also want to match the case where it's one. We also want to match the case where it's several. And the last write that down, shall we? A term can be do we have an example of it? We have a lot of other examples actually. If we look in the if we find a package, there are actually lots of parsers. There's a parser for small talk, parser for HTML, small talk parser. What is it that's comma separated? Tools. Let's load up this parser generator's own user interface that I think we have some way. Look, it even knows about our parser here. Hey, cool. So this is the little custom browser that they have. So actually, we could be doing our development in here. I wasn't because I'm a wimp and I wanted to keep my feet on the ground. But actually, there's a little IDE here. But what we can do while we're here is to see. Here's an expression grammar. Wow, it visualizes things and everything. So when this parsers terms, That doesn't have any concept of something empty. Okay. I have some solution that should work. So terms is going to actually be, it's not going to support the 0 case. It's either going to be a term or it's going to be a term. That's going to be what we had there actually. It's either a term or it's a term followed by some other terms. So it's one or more terms. So we're just going to have to use this appropriately. Term is going to get an instance variable. Terms is going to get an instance variable. So then when we say that a tuple, it is actually a term, but that is optional. Which is to say, yeah, so if terms optional. Unable to parse that. Okay, cool. Anyway, so the idea here is when we parse a tuple, we expect to see an open parenthesis. Then we expect to see one or more terms, which are comma separated, but that's optional. So 0 terms also works because we made that optional. And then we want to see a closed parenthesis. That's what we want to see. And then when we define terms, that's either one term is fine. Otherwise, it can be one term followed by a comma, followed by more terms, which should also be fine, and a single term, string or a list or a tuple. We got to put in a number somewhere. Okay, fine, that looks good. So why did it fail? Unable to parse 42. Oh, okay, one of our test cases had a number. Oh, hey, that's cool. So we didn't have any numbers in our input, but we're supposed to be able to parse them. We didn't have it in our input that we got from Nix. We did have it in the test case that we just hacked up, so that's handy. So we'll parse those, shall we? We will say wonder what's the most straightforward way to parse a number. You actually say you want to parse digits, or is there something built in? Now we can go back to that other example we had. Probably go back into the browser. Pretty cool little browser, actually. I like these things. How do they do numbers? What is a number to them? Okay, they've got a proper production with a minus sign. Okay, fine. We'll just start off like this. We'll say it's some number of digits. That'll do fine. Number. We will say that number is some positive number of digits. Now can we parse? And then we need to say that a term can be a number as well. Instance variable for number. Then can we parse a tuple? No. And there's another thing. So we had spaces in our example, which is probably a good thing. So again, I don't think there were any spaces in the thing we got from Nix, but we may as well handle spaces, right? It's not a bad idea. There is some easy way in the parser to say that something can be surrounded by spaces. Let's pop in. I should stop closing that window and just keep it open. How do you say something? Trim. I think it just says if there's any white space, just chuck it. Fine. So, where's the right place to do the trimming actually? We might want to do that around whatever it is. We'll always trim the term. Is that likely to work? I'm able to parse that. Let me just check if that actually works the way that I think it does. If we had the string space space foo space, and we asked for, and we wanted a parser that would be foo. We had a trimmed foo parser. We asked it to parse that, then would it work? Yes. If we didn't trim it, would that work? No. Okay, yeah, so trim does seem to discard white space. So it seems like that's right, I just didn't use it properly. Why not? We said that a term should be trimmed. We said a tuple is parentheses and inside it's optionally some terms. I really feel like this should not be needed. Let's just do a little bit of witchcraft for a moment. Okay, good. Doesn't seem like the right fix, so I'm glad it didn't work. Okay, why are we unable to parse that? Actually, I think that there's some special debugging support as well. Should we see if we can figure out that? So we got a parse error there. A parse error is a particular kind of an error, right? So I think it's possible that this debugger is actually able to make high-level sense of a parse failure. So if we just click the debugger here is one of these moldable tools as well that can be extended to support specific applications, and I think that the debugger is one of those applications. I just can't remember how you find parsing specific things. We do have some nice stuff here, like the setup and teardown part of the test case. So it's recognized that it's a failed test, showing us how the setup and teardown was done. But we want more. Debug view. Ah, cool. Literal not found. Was trying to parse a tuple. Tried something that failed. I was trying to get an open parenthesis. This is like all the execution paths that the parser took in its search for working parse. I don't know if that's actually gonna. It's kind of cool. I don't know if this is gonna show us what we need. I don't immediately understand that. Hang on, let's hop over here again and see what we can learn about our parser. We ask it, what does the tuple look like? Tuple is, this is kind of neat too. Okay, so tuple should be that and some terms. So what do terms look like? Terms are a term or a term followed by some term. Hang on. Do that comma properly. Let me just check if we did the comma properly. Terms. So yes, we asked for the comma as a parser. Okay. No term. Oh, hang on, let's write a test for the number first to make sure that works anyway. That'd be a good thing to do. Back again. Self-parse rule. Self-parse 42. Oh, okay, so our integer parsing is broken. What did we do wrong? Did number as an instance variable. Yeah. Digit. We want to get a parser for a digit, and then we'll have one or more of those. I don't see the problem there. Where were we here? String is 42. Maybe the size. Something. String size. Ah, sorry. Did I? No, the string is the string 42. No, sorry, I think I did I write the test wrong? I gave it a number instead of a string. Yeah, sorry. It's not meant to be the number 42, that's meant to be the string 42. Can't parse the number. Yeah, that actually worked. Fine. Okay, so now our enthusiasm starts to wane. Now we just want to get this bloody thing working. So let's get back to that. Enable to parse 42, 43, 44. So this parsed okay, and this parsed okay, and this didn't parse. Okay, so let's try simplifying it for a moment to see if that makes any difference. What about if we take off the spaces? Does that parse? No? Okay, so it should be the terms production. That parsed 8 terms, so the one that does multiple terms seems to be broken. What do we got? Get a term. Terms is a term. Or alternatively, a term followed by comma, followed by some terms. Term can include a number. Term drops all white space. What am I missing? I'm able to parse this. Okay, let's go and debug again and see if it can get any light. Text. That's the text we're trying to parse. Debug view. See if we can make sense of this. Literal not found. Open quote. Isn't that kind of saying it can't find the... Must be something basic. Is that really how you express alternatives? Parser. So let's write simpler test cases. Let's write a test case for a term first. Do this just in smaller steps. The terms parse okay. We do multiple terms. That doesn't parse. Try that ever so slightly. More. But that's good to know. No, sorry, that's not good to know. I'm using the wrong production. Terms. So, I mean, I fall into the trap of thinking that this is one of those really annoying, boring, old-fashioned parsers that basically parse in a non-deterministic order. You know, all this all of these old style parser generators. I hate all of that. The lovely thing I think with pegs is that it's basically a, recursive descent model. It tries something and then it tries something else. Everything is sequential. Everything is easy. But you need to take that implementation strategy into account when you write the grammar. So what I've done is that that this side is never going to match, right? Because if it'll always try to match a single term, and that's going to work, right? Because this one also matches a term. So I've just got these backwards. I need to change the priority of those so that first tries to match several terms, and if that fails, it tries to match one term. And now everything parses. Haha. Okay, but that was kind of satisfying, right? So I've wasted a lot of time even writing parser generators and stuff, trying to understand, automata theory and all of that kind of stuff. And that's actually really interesting. So when I was learning programming, you were supposed to learn about automata theory and all of that kind of stuff. And that's just, I've just garbage collected all of that. I mean, it's very interesting, but I don't think it's very relevant. I think that from my perspective, valuing simplicity of implementation a little bit more, and maybe going a little bit more towards the Viet camp without going too close. I like simple things, and I like simple implementation. So I'm really happy at the way parsers have gone in the last kind of 10 years or something, or a bit more. That it's gone from really complicated, very theoretical kind of incomprehensible implementation strategies to really, really kind of simple ones, and just making them convenient. Anyway, blah, 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 blah. That's looking a little bit better now. Now it's like parsing stuff. So should we try to parse our whole thing now? If we do a test for the start, we'll make it a test case. Okay, why not? We'll call it a test of start. Make a test method for that. Test start, and we will take that big long string that we have, and we need that. That's our big test. Give that a method of its own. Oops. Okay. Hold on, but can we cheat? I like cheating. Can we do something like... Is there any easy way to avoid the whole... Base 64 encoded. Yeah, okay. I'm more happy with that. Example will be base 64 decoded. That. So we test parsing that. It didn't parse. Okay, fine. Why not? I'm gonna already regret doing that. Oh, okay, and we've got to hook in that derived thing. Sorry, I don't think we've stitched our grammar together properly yet. We're going to start production. Okay, so it should actually be derived followed by, let's say, followed by a term. We just get one tuple in practice. Or is it not one? Hold on. Go back to where we have one pre-printed, like here. What was the structure of this? There's derive, and then we get a list, a tuple, and that extends all the way through. So it seems like it's derive, and then I think we're just going to get one term. So I think that high level grammar was right. Why did that stop at some point? I think it stopped after 161 characters. Why? Where were we? Ah. Yeah, so I guess it tried to parse and it kind of returned success, but it didn't consume all of the input, which is not cool. Why did it only go 161 characters in? An easy way in this editor to hop in 161 characters. We just paste it into Emacs. I'm sure that you don't have to use Emacs here, but that's what we're going to do anyway. Go to char 161. Okay, that was. Looks fairly unremarkable. Did I get that number right? Again? I think it is saying it only consumed 161 characters of input, so why would it have failed at closing of a list or a tuple? List. It wasn't the first closure of a list or a tuple either, was it? A tuple closed there, a list closed there. Okay, get any more debug information. Yeah, let's just read. Well, let's browse our grammar again briefly. Actually, when we have that other view of it, that's pretty neat. Just see the same thing in a different way. So we start with the graph, derive, and then we want one term. And does it want something after that? What is this? What do other grammars look like with this? Start production. Did we do something funny there? Start. Okay, that looks the same. Okay, so there's nothing obviously wrong there. Fine, we want derive, and then we want a term. Derive is just going to be the string derive. Fine. Might be followed by a space, but the term should swallow that. Fine. Okay, so what does a term look like? A number, or a string, or a list, or a tuple. And a number kind of looks like one digit, although I think to find multiple digits. Ask for a sample. Okay, I don't know how that works. I think there's something here where you can actually get it to generate input for you. Don't need that right now. Okay, so number is some digits. Oh, we got this C thing. Okay, that's a bit magical. Sorry, I said that we would regret this. I think we're at the regretment phase, which is nice, right? Like, regret is not the favorite emotion, but if we're already at the point of regretting the crazy hacks that we did in the beginning, then it probably means that we're getting close to the end. Yeah, so that's total garbage, right? So the list is not just going to skip over all of its contents. That's crazy. It's going to have terms. And a tuple is going to be the same if it isn't already, which it is. Okay, fine. Does the list still work? No. Okay, now it's unable to parse an empty one, so the terms are optional. Quite nice having those test cases. Aha! Well, now the whole thing parsed. And we've taken away all of those crazy hacks. So it's entirely possible that we actually have a working grammar now, which is cool, right? The next step that we need to do is to define a parse tree, and I think that's going to be pretty easy. I think to start with, we could just map tuples onto arrays and lists to ordered collections to give it a straightforward mapping onto Smalltalk. I don't see immediately any reason not to do it like that, so let's do it like that. But the thing we'll do now, which is also kind of a nice thing, I want to cut corners because we're live coding, we don't want to take up too much time, but we're going to do this properly actually. So we're going to actually rename this class to be not a parser but a grammar. And didn't rename the test, unfortunate. Go through the hardship of doing that ourselves. And then what we're going to do is make a subclass that defines the parse tree. So this is just defining the structure of the grammar. And then a subclass is going to also have a method for each of these, but instead of saying what the surface syntax should be, it's going to say what the parse tree should be. I think that we'll find there's an example of that here. Abstract syntax tree. Yeah, so they subclass the grammar with a parser. We're going to do exactly the same. Oh, almost. I don't know if we're so enthusiastic for those tests. It's going to be pretty simple. Let's make a grammar class. Now we're going to make a subclass of Nix ATerm grammar called Nix ATerm parser. I don't think we need those instance variables. I think we're going to inherit them. I don't think we're allowed to have them here. We'll just take all of that away. Now we will say that start we'll just do thing is that we're gonna override that. So let's see what we actually get there. I don't immediately know a better way to do that than to say something. So here's where we have a string. So we want to parse that string. Can we do this now? Can we say Nix ATerm parser new parse self? Can we parse our string like that? Yes. Okay, so the parse tree that we get now is derive. The parse tree is an array, which is a derive, and then it's these things. So what we want to do at the top level, we want to drop this token derive because we just know that it's there. We don't need that in the parse tree. So the superclass method returns an array with derive and then the term, and we only want the term. So the first thing that we're going to do is to say, I think we can just do we can just say that. And how do they do it? Grammar to a parser. I don't mean they're using real objects and stuff. I'll try that. I'm not sure if that's right, but we'll just see if that works. Will we? Yeah. Yeah. Okay. So now drop that derive thing, and we just have the term. So now when we do a term, when we parse a tuple, now it's returning the open parenthesis and the terms and the closed parenthesis, but we just want the terms. So that's easy too. We will just say that when we're parsing a tuple, do super tuple second element. Does that work? Do we then get rid of those? those pesky parentheses we don't want. So no, that didn't work. Okay, sorry. I think I need to do. I think I'm supposed to do a combinator there. I think this is where I'm supposed to say we take that parser and we create a new parser that does the same thing but passes its result to sends the message second to its result. That's how we're supposed to express it with these kind of parser combinators. Yes. Now we have a term. Now we have some terms. The first, this is a list of terms. This is the terms production, and we're getting the commas. We don't want the commas, so fine. How do we do that in the subclass? Maybe we do that in the superclass instead. Oh, hang on. We do this in small. 1, 2, 3, 4, 5. I wonder if we can just filter it out to throw away those commas. It might be I don't know how straightforward that is. It seems reasonable to me. So here we are getting some comma characters, and we don't want the comma characters. So we just take what the parent returns. And we're talking about the terms now. When we parse terms, we want to return, but we want to reject objects that are just comma characters. I'm sure there's a better way than that, but it's kind of nice to have a real programming language, so to speak. So if you can't think of the clever idiomatic way, you just do it the stupid way. That didn't work. Character did not understand value. Why not? Okay, the thing is that it might be a single term or it might be a list of terms. So again, I don't know if it's the right way to do it, but let's just do it, hey? X is just so this is just easier to do in the top one. I'm sure that there's a neater way to do this, but if we've got our terms here, why don't we just make that one always be a list? If we say 42 as array, then we get it in an array with one item. So let's just say so if we only match one term, we're gonna turn it into an array. I think that's okay. I would have preferred to do that in the subclass, but I don't care enough really about that. And then did we need to take away what we had before? Yes, we don't need this tuple thing in the subclass anymore. So we'll remove that because it's only causing trouble. Life better without that? No. Why did Karen reject? Okay, that's still running. Why is that? We got rid of that. No, did we delete the wrong method? Whoops. Okay, let's go back. We don't want this method. I think we deleted the method that we actually want. First we're going to remove that one, and then we're going to go looking in the changes that we've made. Most recent changes. We removed the tuple method. That wasn't what we wanted, so we will. And again, this is quite small talky, right? We removed that, and I want to revert the removal of that. So we're going to get it back because it's keeping each time we change the code, that's a small transaction on on the image, and so we can go back and undo that, which is actually really nice. You know, the Smalltalk environment is totally amazing. I cursed it at both Nix and Pharo. I just curse out the whole time I'm using them, but they're actually fantastic, and yeah, it's just a byproduct. You know, I appreciate them in retrospect, but I guess any tool that I'm using in anger is always the subject of someone else of grumbling, even if it's very, very, very good. So let's get back onto it because we want to get this finished. There's that comma that I didn't want. Okay, no. And the thing is, now we should be able to reject that comma because now we always get an array. So sorry, we did want that method. We're going to put it back. We just want to get rid of the commas when we have terms now. So what we had before should actually be okay. We want to do super terms. Now we always get an array. We ensure that we always get an array. And let's reject. Okay, but not supposed to reject an object, it's meant to reject a predicate. I mean, there's surely a better way to do this, but whatever. This works and it's quite straightforward. But that still didn't work. Choice node. It's written completely wrong. Just the only problem was that was completely wrong. That's how it should be written. So when we do terms, we go up to the grammar, we pass some terms. That gives us an array. We made sure that even if there's only one term, it'll be a singleton array. And then we feed that array into this, you know, closure. This is a Smalltalk lambda with the square bracket. And we tell that array to reject, which is to, you know, negatively filter out anything that matches this closure, which just checks if it's a comma. I'm sure that there's a neater formulation of that. I'm going to stop repeatedly saying that. That looks better. Now we got rid of the comma. That's very good. Oh, hold on. Hey, buddy. You need a book, do you? Hold on 1 second, little fella. Hold on 1 second. My 2-year-old son Theo came in asking for a book, and he got Communicating Sequential Processes by Hoare. So that should keep him busy for, you know, a couple of months or something. Shouldn't be hearing from him for a while. Anyway, we are going now. Home office. It's actually quite nice. Anyway, where were we? We had just successfully gotten rid of the comma. So now when we parse this thing, we get a couple of arrays. Seems kind of promising. So what's in the arrays? Do they look good? This one has got some things that we don't want. It's got some square brackets. So we need to do a similar change when we parse a list. When we parse a list, we don't want to get the square brackets. We only want to get the second thing, the value in the middle, the terms in the middle. Let's try that. I want to make this a little bit almost there. Okay, so we parse our top level thing. We get 2 arrays out. on there. That's supposed to be a string. Okay, so we need to, for a string at the moment, we get both the quote characters and then an array of characters, which is not quite what we want. We want to get a string object there. Yeah. Okay. So when the grammar matches a string, we want the second element. We want that also as a string. Wonder if that's going to give us what we want. It's possible. Let's see. And I guess this is where it would make sense to do unit tests, actually. In the example, they were doing unit tests both for the grammar to make sure that the server syntax is right, and also for the parser to make sure that it returns the right structure. So it would actually make our lives a little bit easier if we were doing this, if we were doing test-driven development. But I'm going to just pretend I didn't say that because I find it boring. Didn't give us what we want. We wanted it. Look at how strings are done in other grammars. Parser. Small talk grammar. Parser say identifier. That's the parser. Where's the grammar? Where's the parser? When it parses. We don't want to construct a token object. I think there's some built-in support in the parser of having kind of token objects that keep track of a little bit of where they came from and that kind of thing. We're just looking for the easiest way to make a string from an array of characters. So when we said as string, it didn't. It printed a string, kind of showing that it was an array of characters. We want it as a printable string, maybe. Oh, okay. Hang on. I think I know how to do that. Is it like this? If we have A, B, C, we say as string, okay, it gives us something we don't want. But if we say string with those characters, no. Pardon me, just trying to figure out how to convert an array of characters. Not really a byte array, is it? It's more like a character array. I'm sure I did this just. All. Yeah, that does the job. Okay, fine. Fine. That'll do. Again, I'm sure there's a more streamlined approach somehow. Starting to look more believable. String now looks like a string. The thing that I would like now is to get this in. I mean, I think we might even have our parse tree now. We didn't do numbers. They're probably not right. I don't know if we have any numbers there. Fix those. But then what I would like the inspector here. I don't want to see this one thing at a time. I don't want to see like click every single time. I want to see it in a tree view that expands out. And a lot of objects are inspected in that way, but how do we, why are nested arrays collections not done like that? I do it that way. We can kind of expand it out that way, but it's not complete. Although, you know, if we know what the ATerm looks like, we can probably make it into a proper class, and then probably probably not the worst idea to actually turn this into a real object. So, what does an ATerm actually look like? If we go back to a pretty printed one that we have. You know, I don't like the pretty printer that much, right? This could all fit on one line. I would like it to be a little more economical with lines. I think what we can get. This one now, we're just gonna make an object that represents an ATerm, one whole ATerm. Here we have a pretty printed one. Shrink it down a bit. Pardon me, just bashing along here, trying to just format things, trying to unpretty print this, halfway unpretty print it, so I can see what the structure actually looks like. You know, this is where if you work with Common Lisp, you can't respect pretty printers like this, right? Because a pretty printer should kind of be aware of the width of the thing that is printing and make dynamic decisions about where line breaks go. Haskell people were probably the leading edge of this, but this one has just done something very boring and naive. Anyway, we have derive, and then we have tuple here. Okay, we have derive, and then got one big tuple. The first element of the tuple is a tuple, which has a list, and then another list. A lot of lists. Okay, we need to find a definition of the ATerm. So where was that comment? Dolman says that he left a link on Twitter. Hang on, let's go over to in another window. I'm hopping over to Twitter to pick up a link to what an ATerm looks like. Okay, very good. Let me pull this over to a window that's visible on the screen. So we're gonna assume that this is what a derivation looks like. It's a tuple, which is some outputs, input sources, a platform, a builder script, arguments, environment, and input derivations. Does that look kind of like what we have in Emacs? Sure, why not? It looks about right. So then, let us make a derivation class. We're very close to having this done, and we're finished Friday, and we can go to the weekend. But let's just get this out the door. So we want to make a class now called Nix ATerm. No, Nix. We already have a class called Nix Store Derivation. Looks like that's not being used, so we'll reuse that actually. Nix Store Derivation. We're going to create. Doesn't have class methods. No. We'll create a method called fromArray. And this will say, if we just pull up again what we had in that browser window. We will just dumping that there for reference. When we make a derivation from an array, we will say outputs are first thing, input sources are the second thing, platform is the third thing, builder is the fourth thing, args is the fifth thing. You see that Smalltalk and Common Lisp are basically two sides of the same coin as far as I'm concerned. I like them both for some reasons. I won't abbreviate quite so much. Derivation. That looks promising. So this is the object that we actually want to return now. We'll every time we refer to a free variable in the source, when it's saving, it says what do you want? Is this a local variable or is it an instance variable or straight, whatever that is? But that everything declared as an instance variable. Now, when we go back to our parser, it was that we had that. When we now we actually want this to be a bit different. Now we want to say, I get that, and then we'll put that into Nix store derivation new from array x. So take whatever it is that comes out of our parser and we'll make that into a Nix store derivation. Can this possibly work? Are we? There. The array that we passed in was too small. Interesting. So what is the array that we get? From array. Oh, we only get a 2-element array. Why is that? We wanted to get a 7-element array. Dot 2-element array. Just okay, so now I want to pretty print this specific derivation that we're looking at, which I think is that one. Okay, so what do we got? We got looking at this, it seems quite clearly like it's a big long 7-element, I assume, tuple. So why did we get a 2-element array? It seems like it seems like our parser returned 2-element tuple when actually it could have been 7 elements. Why would that happen? Let's look at our code and see what we messed up. We do a tuple. I think it's the way that we wrote the grammar. when we, I think it's the recursion here, that we'll kind of build them up like a tree of conses. So we'll get an array where it's one term and the next element is an array of terms and that kind of thing. So actually what we want is the whole thing to get flattened out. Maybe we can just do it there. Can you flatten things? What happens if you say, is there such a concept as flatten? Not really. Anyway, let's do it in a simpler way. When we parse the tuple, anytime that we do that, we actually want to combine those together. I'm just going to take a little hack and slash approach here. Say that when we do that, we're going to want to create not completely satisfying. We want to flatten that out. It has to be flattened. It can't be like deeply flattened out. It has to be only a little bit flattened out. Okay, fine. We'll just do it the simple way. We'll say that your collection oh wow, look. Convenient method with this and with all of these. Oh wow, that's pretty cool. Okay. So we might even be able to just say array with x and with all with the first element and with all of the second, all the elements from the second element. You know, so let's see if it works. If it works, then we'll explain it. Nearly time to wrap up. We're racing the clock here. Where best case. It's not going to work. Yeah. We got that pesky comma there that we don't want. Okay, so the wrong thing there would be the third thing, because we want to get first this term, then we want to skip over the comma, and then we want to get all of those terms. Okay, that's starting to look a little more respectable. We have Nix store derivation. Its outputs are an array around like this. Its outputs are these things. Input sources, these things. Looks like there's a string there that didn't get very properly. That's something like that. Platform. What did that look like? Within a string. Some of the strings didn't get done up nicely. Some did and some didn't. That one looks good. That one looks good. So one of the productions wrong somewhere. I spend a very small amount more time on this, and then I'm going to declare good enough because we're actually really close. We're just dotting I's and crossing T's now. Somewhere, do we have a difference between the way we do a topol, for example? No. That's not nice. Let's say something like that. Any number of characters that are not quotes, not negate. What is it called? You want, when you have a parser and you want to get a new parser that rejects everything the other parser accepted. It would be a method on okay, sorry. It would be that as PetitParser negated. Better. Try this again. Still not looking quite right. Have anywhere still in our grammar one of those naughty things? It's Friday afternoon. I think we're probably close enough. I'm satisfied with live coding for the day. I've probably done like 4 hours, 5 hours of this today. So, what we've done, to recap, we wanted the Pharo Smalltalk environment to understand a little bit better what's going on in the Nix store. So we found a way with Nix, when we have a Nix expression that we want to build that might describe something that takes either a second to build or something that takes like a week to build. So we found a command that turns that into a set of derivations, of descriptions of things that need to get built. What we've done now is written a parser for that in the front end so that we can go off directly into the Nix store, and we can kind of spider our way through as much as we care to find everything that is relevant to a particular build that we want to do, and then we'll be able to kind of poll these things in real time and see what is there, and what is already present, what hasn't been built, what is currently being built. We could start pulling log output from things that are currently being built and everything. So what this is a first step towards making the user interface actually have a kind of a deep understanding of the Nix store in order to communicate that understanding to us when we're running a build or something like that and we want to see the current status of things. So we found this super duper internal format that looks like this, and we didn't immediately find a tool for converting that into JSON or XML. We found a couple of parsers for it in other projects that didn't seem to especially suit our purposes, so we just sat down and wrote a parser, and we've almost got it finished. Our parse tree is not looking quite the way that we want it to, but it's actually very close. So there's probably just a couple more bugs like the one that we just fixed. But we'll do that sometime when we have a spare moment. For now, I wish you all a pleasant weekend, and I have to attend to some other things. Cool, this was fun, and I really like, just in closing, I really like this this PetitParser2 and a lot of this stuff coming out of, it's another one of these tools coming out of the University of Bern. I think they're doing really good stuff in development tools, so I really recommend checking that stuff out if you ever need something like that. Bye bye, thank you very much.